Assalamu alaikum. This is Dr. Usman Sadiq Paracha, and we would be having our lecture number 23 of the subject Applied Quantitative Analysis and Practices. Previously, we were going through our topic called regression, or to be more specific, it's called simple linear regression. In this case, we had a brief discussion about what is the difference between correlation and regression. We discussed about what is the major discrepancy of correlation in this case. For example, correlation gives us a brief idea of whether a relationship exists between two variables or not. And to some extent it does gives us an idea of the intensity of the relationship, but it is unable to tell us that what would be the cause and effect between those two variables. So this is the major discrepancy in correlation which it is unable to address. However, regression here do facilitate us in this case, and it is able to point out that what would be the predictor variable in this case and what would be the dependent variable in this case. So in this case we do have a clear indication of cause and effect in this whole analysis, and that is why regression is quite much preferred, though correlation has got its own advantages, and in order to have an initial know-how of the whole relationship, it's important that we do perform a correlation analysis. Then we had a discussion on the scatter plotting of correlation, various types of relationships, how do they portray in different scatter plots, and what's the difference between strong relationship and weak relationship scatter plots, and specifically when we are trying to study the correlation in between them. Then we had the introduction that what is simple linear regression, and then what is the model basically, and likewise we had a brief discussion on the methodology which is followed. You would just have a brief go through all these, what is the interpretation and measures of variation. So we just having a recap of what we had studied. This was the model which we discussed, and basically this was focused on a linear function which can exist between any two variables, and again the main concept was that changes in the dependent variable are related to changes in independent variables. So both of these two are related to each other. We have to track these changes, and regression model is one effective tool to help us detect that. In this case we just took the example of what could be the training variable here in this case, as you can see here, and in this case we had just portrayed its impact on employee productivity, and it was termed as dependent variable. Again, there can be multiple independent variables and multiple dependent variables, but specifically in simple linear regression model we have to be focused on a single independent variable. That's why it's called simple linear regression model. So based on that, then we had a discussion on what would be the mathematical form of this thing, because technically speaking we just plot this whole thing in the form of a diagram which is like this, in form of x and y, and we just plot these values on both the axes, and then when we have to comprehensively describe this relationship, we just draw the line in this case, which is the ideal relationship in this case between x and y, and then we can basically portray or idealize these observations in the form of a line. But again, in this case, in order to describe this line in the form of an equation, we just discussed this, that ideally what you might have studied in previous grades, that this was portrayed in the form of this line called y is equal to mxc, where m used to be the slope here and c basically here portrayed the intercept. So here we are just portraying the same concept in other words, and here we discussed whether the dependent variable here was portrayed as yi, then again the intercept was portrayed here in the form of beta naught. Likewise, the slope coefficient was portrayed as beta 1. Then we had our independent variable in the form of x, and then we have an error term called eta here. So this basically linear regression model mathematically then is termed in this form, with having a linear component here and the error component, because ideally we cannot portray the whole line in the same form, but we have got certain errors here. So if we go in detail here, we can see that if the all individual variables, the individual observations are magnified, then we can see that these one, for example, value which we discussed before, observed value, can be measured with reference to the predicted value, and we clearly discussed that what is the graphical representation of the error term here, and likewise how we can represent the slope here, and the intercept was also portrayed. The same equation basically, which you can see here, y is equal to beta naught plus beta 1 xi plus eta, is portrayed here. So we discussed about the graphical representation of that same equation, and again this was one important point, that we cannot just find simply the sum of these values, because the values which are on the positive side, which you can see here, this one, or this one, would be basically neutralized by these negative values which are here. So that's why we have to basically take a certain methodology to find out the sum, and that's why we take the sum of squares of these values, so that these positive and negative values do not neutralize each other. So this basically methodology of taking the sum of square of all these values has got a certain name. Again, here we are portraying the same equation but with smaller b, because this is the estimate basically here of the sample, so we are portraying it with small beta naught and beta 1, and we discussed about that with this estimate here. Once we have gone through that, then we had this method which we discussed before, that how to basically calculate the sum of square differences. So the sum of square differences phenomena is calculated in order to avoid this nullification of these positive values with negative values if we take the simple sum of the values. So we have to take the sum of square difference. So this square difference basically gives us an edge in finding out a real-time value which is not nullified, as we have discussed before. So this methodology is also termed as least square methodology. There are other methodologies as well basically which are followed in regression, but normally the most common method which is followed for simple linear regression is least square method. So here we discussed about the representation, that what is meant by beta naught, which basically is the average value of y if x is 0. Then beta 1, that's the main value which is of major importance to us, because it's the estimate change in the average value of r if there is 1 unit increase in value of x. Mind you that the change basically is calculated with respect to the average value of y. So whatever calculation which we are going to make would be based on the average value of y, and even we would see in further slides that all the graphical interpretation is also done with respect to the average value of y. So that's of major importance. So then we had another important concept which we discussed in an example. We took an example of house pricing and how it impacts on the size of the house. So in that we just basically put the values in the software, and when we graphically portrayed these values, basically here as you can see in this form, which is portrayed here. So the scatter plotting basically gave us a brief idea of the values which are concentrated, and then we drew the prediction line. As we can see, we have already discussed in SPSS, and we will do this again, how to draw this prediction line in SPSS. So the slope of the line is portrayed here, which you can see in this form, and then we have the intercept, and in equation form you can clearly see we depicted it in this form. So the important concept which we discussed was that if we want to find out any value, then we can find out the values in between these two extremes. We cannot go beyond this. We cannot try to find out the value of any thing here beyond this extreme, because then, in other words, we are trying to predict, and basically regression is not about predicting, it's more about explaining the phenomena. So explanation basically can be done of any points in between these two extreme values, which you can see here. So this was the concept which was important, and we discussed about it previously. So going through that, then next we had this is again the interpretation of the same concept which we discussed, that we do not extrapolate beyond these limits which we have just discussed before, and that's an important part basically. Then we had discussed about the various measures of variation. Now this is a very important part here, that the total sum of squares, which we had discussed before, comprises of two concepts, and one is the regression sum of squares, which we can see here, and it is denoted by SSR. Then we have an error sum of square, which is denoted by SSE. Now both of these parts, when combined, form the total sum of squares, and their relative formulas are enlisted here beneath them, and the notation here you can see here is shown here in this case, where y bar basically is showing the mean value of the dependent variable, then yi is basically the observed value of the dependent variable, then yi prime here is the predicted value of y for the given xi value. So here basically now the explanation of the measures of variation was given, which we discussed before, and the main concept which was important was that SSR gives us the explained variation, the variation which is totally explained by our values which we have been given. But then there is some part which is not explained, and that is termed as SSE here. and also termed as unexplained variation or error sum of squares. So when these two are combined, then this our SST part is formed, which is total sum of squares. Measures of variation basically is an important concept, and we would see ahead that how it explains the whole phenomena of regression, and the whole regression process is dependent upon these two key values which we have been discussing. So going through it graphically, let's have a look at it. Here you can see that our typical line here is shown, and the mean value y is shown here, which you can see in this part. Again, as we have discussed before, that every value of x would be with reference to the mean value of y. So that's why we have drawn this mean value of y. Now every calculation of even measures of variation would be taken with reference to the mean value of y here. So here is the total sum of squares of the individual value. Now here this dot is the individual observation which has been done. We have just magnified it. And here we can see that the total sum of squares can be found out by summation of each individual variable minus the mean value of y, and we can take the square of that. Then the part which is in between the line and the mean of y basically is the part which is clearly explained by our model, and hence it's called SSR. That's why it's called sum of square related to regression. So this is a part which has been clearly explained by our model, but there is some part which we are not able to explain, and that is the part which is here defined as SSE, which is sum of squares with regard to errors. So here basically this total part is not, SSE is not being explained by our independent variable x. This part can be due to the interference of some other variable which we may not be considering in our this present equation. So this variable x is able to define only this part of our deviation in y. So here you can clearly see the error part is more and the explained part SSR is less. So anyhow, this is a graphical depiction of how we try to calculate this explained part and the unexplained part here. So that's why measures of variation is a very important concept while explaining the regression phenomena. And once we have gone through this exercise of calculating the regression part and the error part, we can then easily explain the total sum of squares. Then our next concept is based on these two, and which is the sum of square of regression and sum of squares or total sum of square. This part is termed as a coefficient of determination, also termed as R square. Now it's the portion of total variation in the dependent variable that is explained by variation in the independent variable. So it's basically calculated by dividing the SSR with SST. So basically we are trying to find out the portion of, as we have seen, that the variation which has been explained by our independent variable, and that is when divided by total sum of squares, it gives us a figure basically, which in other words would tell us that to what extent independent variable has been able to explain our total dependent variable in this case. So again here R square value ranges from 0 to 1, and again as a rule of thumb it's if it is greater than 0.5, then that is kind of significant explanation by a single variable. And this, in other word, this is R square is also termed as coefficient of determination. So coefficient of determination is a very important concept. It is the key concept behind regression, and our whole regression process is explained by this 1 R square value. So based on that, then we can see here that the scatter plotting of R square is the same as we have done it in scatter plotting, and we are given the value of R square in scatter plot as well in SPSS, which basically the calculation of which is done in the background. So basically in this case ideally we are here seeing that when would R square would be equal to 1. The scatter plot here you can clearly see here that it's in the form of straight line, but again this is a very ideal relationship and normally it's not possible. This is R square here is 1 in both cases, but in this case, in the top one, R square would be -1. And then here in this case downwards we can say that it's the positive relationship between the positive and negative in the case of independent and dependent variable. So 100% of variation in y here in this case is explained by variation in x, which basically is very ideal case. Normally in real time scenario it does not happen. So then we have another case in which we are studying the weaker relationships between x and y, and then again R square in this would be ranging in between 0 and 1. So here again in this case this is an inverse relationship in which we would be seeing the negative relationship basically in between x and y. We have already discussed this before, and in this case with this line and the pattern in this form, then we have got a positive relationship. We have discussed this with within context of correlation, but again R square in both cases is reported in SPSS, as we will discuss it again ahead. So then we have got another situation, we have discussed this before, which is that what would be the case in which R square is 0. That is, there won't be any relationship. So graphically this whole relationship can be portrayed in this form, and in this case independent variable x has not been able to explain y at all. So R square would be 0 in this case. So these are various examples in which graphically we can portray the values of R square, which can range from 0 to 1. Then again they can be positive and they can be negative as well. So regression can report positive value as well as negative value as well. So coming to this thing, this is the example in which R square has been calculated in a software and these values have been portrayed. Now here you can see that R square is shown in this form and its value basically is 0.58. The calculation has been done through this R square value, which is shown here, SSR, which is this value, and then there's a total sum of square which is depicted here, 32600, and this value can be shown here through SST. So we have just taken the ratio and R square value is shown here. Again, 58.08% of the variation is shown here. So that means that our independent variable is able to explain 58.08 variation in a dependent variable, which is the house prices in this case. So the coefficients here can be seen, which are shown here, and then the intercept is shown here in this regard. The rest of the values we will discuss again ahead, that what is the significance of these values which we have calculated here. But here the main thing which matters is the regression value, which is shown here through SSR, in fact, which here you can say SSR, and here total value here, this can be termed as SST. So we have just calculated it, and in mathematical form this R square is shown in by this value here. So this is a very simple depiction of how the software gives us the various values of measures of variation, and in the background how they are calculated there. So coming to the next part, the standard error of estimate here. Now here basically it's the standard deviation of variation of observations around the regression line, and you can see here that we basically are trying to find out the standard error of this line, basically of variation on this line. So the whole thing is calculated around this line. So coming back to the point here which has been made, so this variation has been calculated of every observation around regression line, and in advance we basically are trying to find out the standard deviation of this variation. So standard deviation of such has been given by this formula, which you can see is portrayed with SSE divided by n minus 2 here, and if we give into more details, so you can clearly see that summation of y I minus y I prime square is represented by SSE and divided by n minus 2. So standard error of the estimate basically is another concept, which is we are basically trying to standardize the errors of the estimate which we are trying to calculate here, and n here is the sample size. So you can see that here in results, this is the value, sorry for that observations are 10. Basically this is the value which is portrayed here in the form of standard error, and it is important that this standard error should remain low. The lower is the standard error, the more accurate is R square, the more basically R square would be able to depict our values in dependent variable. So this standard error value should be lower, and that's the key criteria in this case for more explanation of dependent variable, as we have discussed before. This concept is important, and basically we have standardized the variation of these of our error estimate. So standard error estimate is another measure which can point us in the direction whether our analysis is really giving us the relationship which we are trying to prove, because higher standard error will automatically affect the R square, and then if the R square is affected, that means that our independent variable impact on dependent variable is not that much in this case. So R square and standard error of estimate both are related to each other in this case. Coming to the next part, how would we be graphically portraying this standard error here in this case? So here you can see that in case we have got small standard error, which you can see here, in which the values are closely knitted to our ideal predicted line. So in this case, by default, the standard error would be small. But if we have got large errors in there, then definitely this error, for example, for every point, if we start plotting them, and then if we try to find out some composite of these errors, definitely the standard error would prove to be larger in this case. So the more the values are away from the predictor line, the more higher would be the standard error. So that's why the standard error comparison is made here, that in which situation would be the large error, which you can see here, and basically the points, the data points basically which are away from the line, in fact increase their distance from the line, and thus their values are increased, and in advance then they also impact the magnitude of the standard error. So here basically how can we judge the standard error in this case? So we have to basically judge them relative to the size of the dependent variable values. So here you can see that our standard error has been proved to be 41.33K. Now this is compared to as compared to the Y values, it's small, because let's say if we come to the original data set, which basically ranged from 200 to 400 values, now if we have a look with that, then standard error is quite smaller. However, if our value of standard error had been greater in terms of these range values which are here available for Y, then again it would have been clearly depicted that the standard error would have been larger in this case. So basically it's not just about portraying the standard error estimation and try to see that whether this value is larger and smaller, because we have to basically compare this value of standard error with dependent variable values, the normal dependent variable values. So only the benchmark of dependent variable values of Y would be helping us in deciding whether our standard error is small or whether it's large in this case. So here basically in this case we up till now have clearly learned that R square value is equally important and it gives us the strength of the relationship, but along with that the standard error of the estimate is equally important, and it greatly impacts our interpretation of R square. So the same diagram, graphical representation of the values which we have done before in terms of correlation, in terms of scatter plotting, and also in terms of regression as well. They not only tell us or gives us information about R square and the strength of relationship, but in advance they also gives us a faint idea of how much would be the standard error. So basically both of these values give us a fair idea of the nature of relationship which may exist between independent and dependent variable in this case. Then we have another issue which is regarding the assumption of regression. Now there are certain conditions which must be met before we commence with that. So here basically, after we have gone through this regression phenomena, some additional results are required which would validate whether our regression process was validated or not validated. So these conditions, as you can see here, are related to linearity in terms of independence of errors, normality of error, and then equal variance, also termed as homoscedasticity. Now here we would just discuss them briefly. We would also have a detailed discussion on them in future lecture. Then what is meant by these conditions? So by linearity, one condition is that the relationship between independent and dependent variables should be linear. Then likewise, it's important that these error values should be statistically independent of each other. And basically this condition is also termed as independence of errors in this case. Then third is the normality of error, and normality of error depicts here that the error values are normally distributed for any given value of x. So it's very much important that the error values are also the residual values which we have discussed before. They should also be normally distributed. So you shouldn't confuse it with the normality condition for the variables which are very much inducted at the very start. And basically for that condition, the individual variable, each individual variable should be basically normally distributed. Now that is another condition. But not only the variable values which are being inculcated at the very start of regression, not only those values should be normally distributed, but also their errors or the residuals which are created after testing regression, they should also be normally distributed in this case. So this is an additional condition for normality, and we would discuss that these residuals, how they are measured in SPSS and how they are depicted in our analysis in this case. Then another important condition which requires our attention is termed as equal variance, and here it's termed as homoscedasticity. And again, it's important that the probability distribution of the errors should have a constant variance, and that is very important in this case. So equal variance basically is advocacy basically for the probability distribution of the errors to be normal, and it should have a constant variance as we have discussed before. So now here, coming to the residual analysis part, because once we are discussing about our conditions, you must have noticed that most of the conditions are related to the errors which are there in the regression analysis. So that's why that gives rise to totally another form of analysis which is also termed as residual analysis. And here you can see that the residual analysis here basically is represented by E, and this is basically the depiction of y prime, which is subtracted from the y value. Now it's the difference between the observed and predicted value, but that's the residual which is calculated for any single observation. And we have to basically find out the linearity assumption for these residuals. We also have to evaluate the independent assumption, and we have to ensure that they are normally distributed as well. And then we have to see that they have a constant variance for all levels of x. So also we go through a graphical analysis of residuals. So we have to plot these residuals against the relative values of x. Now, as we have discussed before, that the conditions which should be met after the regression analysis has been performed are specifically related to the errors or the residuals here, and which is an important part, because not only we have to ensure that the variables which we are entering in the regression analysis, not only are they normally distributed and not only their conditions for regression are met, but also the conditions which are important after the residual after the regression analysis related to residuals, they must be met too, because violation of any of these can again depict that our regression results are not accurate. So coming to the next part, this is just the depiction of residual analysis for linearity. Here we have plotted the residuals, but again we would be discussing in detail afterwards that there are different types of residuals which are calculated. For example, standardized residuals, because normally the error terms which we are calculating from original values, they cannot be compared with each other. So that's why we standardize these residual values by dividing them with their standard deviation. Once we have got the standardized residuals, then we are very much clear about which residuals are within the normal range and which standardized residuals are not in the normal range. So we would be discussing that in detail afterwards. So coming to the graphical plot, if we plot these standardized residuals against their predicted values, which are again the standardized, then basically these graphs basically here, as you can see that the standardized residuals, which are also depicted through z values, if they are plotted against z predicted, that means that the z values of y, then the values which we get, if they are in this form, which you can see are forming a curve here, then that means that these residual analysis is not giving us a linear form, which is also depicted here. So this is the kind of residual analysis which is not required. Likewise, if we have got this form, which is depicted here, then this kind of residual analysis is acceptable, and we do meet the condition for linearity of residuals, which we have already discussed in this case. Then we have got another form which you can see here, even if the residuals are plotted in this form, which you can see here, even then the basically the plot between these residuals is considered linear, and the condition for the regression is met. Then we have got some additional issues that how we can depict that the values are independent or not. And here you can see that once these values are plotted, this depiction here clearly gives us the notion that the residuals are not independent. And likewise, if you can see the pattern here, which we can see, then again the residuals here clearly depict that these values are not independent. In case of independence, and in order to prove that these values are independent, the pattern should be in this form, which you can see here. So how to get these things plotted in real-time analysis would be discussed later, but theoretically how these different patterns of these residuals are available are shown here in this slide. So after when we have gone through this residual analysis, then we have to check the important part, and that is the normality part. Again, the tools which we have are the same which we have used for checking the normality of our individual variables of the original data set values. Now here you can see that stem and leaf display, again we have discussed this in detail, that this tool again is calculated, but the difference is that now we are trying to find out the stem and leaf display of the error terms and not the original data set values here. And again that display should depict normal distribution. Then we have got the box plotting, and again the box plotting of the residuals should again depict normal form, and we have discussed in this case that the box plotting diagram is in this form, which you can see here. And just to give us a clear picture, this is pretty much evident that the mean value should lie in the middle, and the distribution for these residuals, in order to portray that this is normal, that this kind of box plot diagram should be there. So this is the ideal box plotting pattern which should be there for residuals as well. Then we have got the histogram of the residuals, which should be basically portraying normal distribution. Again, we have discussed this before, that in case of a normal histogram, this is the typical kind of diagram which should be depicted here in case of a normal distribution of residuals. And if we draw the curve should depict a normal distribution curve. So again, the histogram of the residuals should portray the same normal distribution which we have discussed before. Then we have got the normal probability plot of the residuals. Now again, the plot is also termed to be PB plotting or QQ plotting. Both are the same thing. And in this case, as we have discussed before, that we have got a straight line, and the residuals should be closer to that specific line. Now the farther the residuals are from that specific line, the more abnormal is the normal probability plot, and that basically gives us an abnormal notion, and which would violate the normality condition for regression. So these are basically the same tools which we have discussed in terms of individual variables, and basically the formulation is the same, but the only difference is that in this case we would be more focusing on residuals, as we have discussed before. And then we have got the residual analysis for normality. Now here you can see that the normal probability plotting, as we have discussed before, is depicted here. The residuals are plotted in x-axis, and then they are normally depicted in terms of percentage, and if we draw that line, we can clearly see that these errors should lie along that line. And as we have discussed before, the farther are the errors from this line, the more abnormal is the normality probability plot, and that basically gives us an abnormal set of values which would violate the condition. So now here we have got certain analysis part for equal variance. In what conditions would we be basically facing the equal variance, and in what conditions we would be having a non-constant variance. Here you can see that if the residuals are portraying this kind of pattern along that straight line, then we have got a non-constant variance. Similarly, we have got another pattern which you can see here, and this basically pattern gives us a clear indication that there is a non-constant variance which is existing, and this again clearly depicts the violation of the conditions which we have discussed before. So these kind of patterns should be closely monitored. Normally it's not possible that these patterns are very idealistically portrayed in the diagram, but if the values are even close to forming such kind of pattern, then this clearly means that the residual analysis is violating our one important assumption which is related to equal variance. Then if we want to have to know that what's the ideal pattern for showing constant variance, so you can see here that the values of all these residuals and the plots are along that specific line, which gives us a clear portrayal that there is a constant variance existing. Then we have got another pattern which is in the form of a straight line, and basically residuals are lying here close to that straight line. So again, this kind of depiction shows us a very constant variance phenomena here. So basically these are the patterns which should be strictly followed while assessing these various normality conditions. And then this is just one example of the residual output of our same example which we have been doing for our house prices. And here you can see that the residuals have been plotted, and here you can see that they are lying kind of straight, and they are kind of lying along with the parallel line. They are not depicting the pattern which we have discussed before would be clear notification of violation of regression assumption. So these types of plots are vital for giving us the clear-cut idea whether the conditions which we are trying to meet are really being satisfied or not. So here the residuals again are calculated. As you can see, their values are also portrayed in the form of table. Obviously in SPSS we have to calculate them through another way. Here they are manually calculated and basically given here in the form of a table. So basically this example was just to give you a brief example of how a set of example can be clearly not violating the regression assumptions and satisfying the regression conditions in this case. So then we have got certain issues regarding inferences about the slope. Now we had discussed about the standard error, but there are standard errors separately calculated for the slope as well. And here you can see that the formula for the regression slope of coefficient B1 here is shown here. The formula for that is clearly depicted here in the form of SYX and SSX, and the values can be easily calculated from the formula which is here. The SYX, again, we have already discussed, is in the form of standard error of the estimate. Now, standard error of the estimate formula has already been discussed to you previously in this case, and here the estimate basically of the standard error of the slope is depicted by SB1. So we have to calculate the standard error of every regression slope here as well. And again, the greater is the error, the more problematic it would be for our regression issue. So in today's lecture, we discussed about the measures of variation, but we discussed that from graphical perspective, how these various measures are graphically portrayed and how they are graphically measured. What's the concept behind the sum of squares of explained variance, and then sum of squares of regression, and then sum of squares for errors, and what's the concept behind total sum of squares. We discussed that in detail, how these various factors when jotted down in graphical form can give us a clear picture of how regression process is run. Then we discussed about a very important coefficient of regression, and it's termed as coefficient of determination. And we discussed how this R square is calculated and how the values of SSR and total sum of square can affect this value. And in this case, the R square value ranges from 0 to 1, and then again R square value basically gives us, in fact, the strength of the whole regression phenomena. And that's why the measures of variation here in this case play a very important role in getting this coefficient of determination calculated. Then we had the examples of how a coefficient of determination is portrayed in different kind of scatter plots, and in what different conditions in scatter plot R square value would be equal to 1, or would be equal to 0, or it would be in between 0 and 1. So these were different states in which we just discussed that these kind of scatter plots would be depicting this kind of R square value. So R square value again is of vital importance. That's why the measures of variation also get their due importance based on that, because R square calculation is based on measures of variation in this case. Then we had a brief discussion about what is standard error of estimate. Now we try to calculate the errors of the estimate values which we have just encountered, and how they are standardized, and then how we are calculating them. Then the important perspective is that once we have calculated one value, then how can we say that this value is smaller and larger, and what would be the criteria for accepting or rejecting this standard error of estimate. Now in this case we discussed that the standard error of estimate figure should be compared with the values of dependent variable. Now if the range of dependent variable values, if the standard error estimate falls within that range, or even it is smaller than that range, then we can say that yes, this standard error estimate is smaller. But if this standard error of estimate value is going beyond that range, then we say that standard error of estimate is definitely quite larger. And then again we have discussed that coefficient of determination and standard error of estimate, in fact, are quite much related to each other. And that is why this is quite important, that standard error of estimate should also be low in order to have a clear depiction of an idealized regression case in this case. Then we had discussed that there are certain conditions for regression which need to be justified. And in this case, this is quite vital, that these conditions like linearity, independence of errors, normality of errors, and equal variance of errors are quite justified. Now the difference here is that just like we had tried to justify the conditions for initial data set values for each variable, the same phenomena is repeated here for the errors of these regression variates as well. Now these analyses are generated after the regression analysis is conducted, and it is quite important that this linearity of errors is again justified, because again the errors should be linear in this case again, and then again these errors should also be independent. Now in case of linearity, we are deploying all the same tools which we had employed previously for detection of normal distribution in individual data set values, and here we are using the same tools like stem and leaf display and histogram and normal probability plotting. So all the same tools are used here. The only difference is that then now we are using these tools for residuals in this case. Then we had discussed what is the independence of errors and what would be the patterns basically which would depict that there is the independence of errors in the values which you have just conducted, and those patterns in which would clearly depict that there is no independence of errors there. Then is the fact that there is normality of errors. Now how to measure this normality, and whether we have got this normality factor like measured through normal probability plotting. The rules are the same, that these errors should be along that straight line, and if they are farther away from that line, then we have got this normality of error condition violated. Then how to basically measure the equal variance part. Equal variance again is also termed as the homoscedasticity, and in this case the probability distribution of these residuals should be normal, and we discussed about the patterns in which this equal variance is clearly depicted as the value which is not justifying, and again we would have to justify this factor here if we want the conditions of regression to be met. Then we discussed about the inference about the slope, because the slope like beta 1, it also has its error values, and these standard error is basically calculated for slope, and again if this value is higher, then we have got trouble in the regression values as well. So this is calculated by certain formulas which we have discussed in these presentations. So inference about slope gives us the notion that it's not just about the standard error of the estimate for the whole model, but also we would have to calculate the standard error for the slope as well, and this basically comprises of important assumptions which should be met overall and should not be violated at any cost. So this was related to the lecture which we have discussed. I hope you have understood them. Thank you so much. Allah Hafiz.